Okay, so describe the motion practice. The way this one works is we have a data table, okay? We have graphs, and then we're going to fill out 3 boxes for each. The first one's done for us. So, X versus T. That X means position. All right? So a position versus time graph, which is the same thing as like a displacement versus time graph. All right? Which is also the same thing as a distance versus time graph. All right? So position on our y-axis, time on our x-axis. Okay? So the first column, we describe the motion depicted by the solid line. So here's the solid line right here. The body is at rest at some positive position. All right, there's our description. Okay? And now, B, how, if at all, is the motion depicted by the dash line different? All right, so we have the dash line down here. Okay, what about these two motions is different? Well, the other body is at some negative position. All right, and then C, how, if at all, is the motion depicted by the dash similar? So the dash line, how is this motion and that motion similar? They're both at rest. Okay? Fairly straightforward. Next graph. How would you describe the motion of the solid line? I want you to think about it for about 3 seconds. Notice it's a position versus time graph. All right, so that right there, how would you describe it? Is it at rest?
No.
All right. Is it going up a hill?
No.
No.
Of course not.
Okay. What is it doing? Is it accelerating?
Wait, what graph is this?
It's a position versus time graph, which is like a displacement versus time
It's
graph.
not accelerating.
It is not accelerating. It's linear. In a position versus time graph, linear means constant velocity. What else can you tell me besides its constant velocity? All right, well, besides fast or slow,
Positive.
what is positive?
Up.
Positive direction. Positive direction, which means it's moving either to the right, or it's moving north, or it's moving up. Okay? So positive direction, we'll just say moving to the right. Okay, so what's different? The dash line, he's moving faster. Steeper slope. Yes? What's similar?
Positive. Positive direction.
All right, they're both going the positive direction. They're both going in the positive direction. Okay? So, they have different speeds, but the same direction. That might be helpful thinking of it that way. Different speeds, but same direction. All right, next graph. How would you describe the motion of the graph with the solid line?
Negative.
All right, what's negative here?
Down.
Is it going down a hill?
Yes.
No.
Negative direction.
Negative direction. So it's moving like to the left. What is that motion? Is it decelerating?
No.
No. This is a position versus time graph. So what does a linear graph mean in a position versus time graph?
Constant velocity.
Constant velocity. The dash line. How is this one different from that one? What's different about this one?
Oh, it's in a negative position.
All right. It's in a negative position. Another thing that's different about it is where it starts. Where does it start? Where does the dashed line start? At the reference point. This one starts in a positive position. This one starts at the reference point. Okay? So what is similar? Well, they're both moving in the negative direction. They both have a negative slope. They're both moving in the negative direction. What else is similar? All right? They both have the same speed. They both have the same slope. So if they're moving at the same speed and the same direction, they have the same velocity. But wait a second. How could they have the same velocity and not be the same graph? Because they're starting in different positions. All right? This is like two people marching in a line. All right? One slightly in front of the other one. They're going the same speed. They're going the same direction. Just one's a few steps ahead of the other. Let's just describe the solid line. So ignoring the dash line.
Starts in a negative position.
All right. Starts negative. I agree. How would you describe the motion? The motion.
Constant velocity.
Constant velocity. What else can you tell about that motion? Positive what? Direction. Okay. So now looking at the dash line, how are these two different? What direction is my dash line going? Negative direction. Is that opposite? Yes, that's different. Negative direction. All right, is it a constant velocity?
Yes.
Yes, it is. So that would be something that's similar. Constant velocity. All right. Is there anything else that's different?
Yes. Starts in a positive position.
This one starts in a positive position. Dash line starts in a positive position right there. Besides the fact they're both a constant velocity, is there anything else that's similar?
Same velocity.
All right. It's not the same velocity.
Same speed.
It's the same speed. That slope and that slope are the same, except that one's negative, one's positive. Do you guys see that?
Yes.
It's the same slope, just one's positive, one's negative. So they're going the same speed, but opposite directions. Same speed, but opposite directions. So you have two people walking at the same pace, but going opposite directions. All right? So here they're walking towards each other, they cross paths, and they walk away from each other. Cool? All right. Next one. Describe the motion of the solid line. So in your own words, right now, give it a shot. Write it down. Describe the solid line in your own words. Starts in a positive position. All right. It has a constant velocity.
Negative direction.
In the negative direction. I like it. All right, what's different about the dash line? It starts negative. And what else? It's going in the positive direction. And what's similar? They both arrive at the reference point at the same time. So they're walking closer and closer and closer to each other and they stop at meet the reference point. All right, so coming from opposite directions to arrive at the same place at the same time. All right, now to the backside. Describing the solid line. Notice here. Here's the big note. Pay attention. We have now just changed the type of graph we're looking at. This is now a velocity versus time graph, not a position versus time graph. Okay? So in a velocity versus time graph, here we have the solid line is described for us. The body is moving at a constant speed in the positive direction. Okay? So, the dash line. Think about what the dash line's doing compared to that one. What's different? He's just got a slower speed. How are the motions similar? All right, they're both a constant velocity. And there's one more thing. Notice on our axis here, this is the velocity, and this is time. Everything in this quadrant is a positive velocity. Everything below it would be a negative velocity. All right, I don't show much in the graphs here in the negative velocity. It gets a little bit too complicated, but if they're both positive velocities, what do you know? They're both moving in the positive direction. They're both moving in the positive direction. Okay? The next graph is also a velocity versus time graph. See if you can do it. Okay, were you able to describe the solid line? Velocity versus time graph. We have a slope here. Ooh, there's a quick review. What does the slope mean in a velocity versus time graph, class?
Acceleration.
Acceleration. So, how would you describe this slope in mathematical terms? So, what kind of a slope? Negative. So, if we have a negative slope in a velocity versus time graph, how would you describe the motion of the object? Decelerating. Decelerating. That velocity there on our y-axis is getting smaller and 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 smaller. It's going slower and slower and slower and slower and slower. What happened right here? Its velocity became what? Zero. Decelerating to a stop. How are the motions different? It says that the other body, the dash line, speed is changing more rapidly. All right. So it's decelerating as well, but that changing speed is changing. The velocity is changing. That's the definition of acceleration and deceleration. The velocity is changing. The dash line is just doing it faster. So they both started at the same velocity. This one decreases velocity in a very short amount of time, and this guy took a lot longer, much more time to do the same decrease in velocity. He slammed on his brakes. He just gently pushed on the brakes. Okay? Do you see that? All right. So, how are the motions similar? I already said it. How are they similar?
Decelerating.
They're both decelerating. Can you tell me anything else?
Both stop at zero.
They both stop at zero. Or at rest. Okay? What else? Anybody got anything else? They both have the same initial velocity. Right there, they both have the same initial velocity. Cool? All right, next one. Give it a shot. See if you can fill them in. Notice again, it's still a velocity versus time graph. Still dealing with velocity versus time graph. Velocity on the y-axis, time on the x-axis. Okay, so how would you describe the solid line, the motion of the solid line? Velocity versus time, what's happening? Decelerating to a stop. If you look at that, those two, almost identical, both velocity versus time graph. What is different about these two? All right, this one's decelerating, that one is doing what? That positive slope in a velocity versus time graph tells us what? Accelerating. Okay, accelerating. Okay, what do they have in common? Sorry, is that they both have a changing velocity. But there's more than that. They're both changing at a similar rate. Just one's positive, one's negative. Okay? So as this one, its rate of acceleration is the same as his rate of deceleration. This one's negative and that one's positive. Does that kind of make sense? See, those are similar slopes. Okay? This one you could say accelerating from rest. So he started at rest and he ends at rest. In number 9, you need to notice that this is now a position versus time graph. We just changed back to position versus time graphs. Okay? Position versus time graph. Right here in the solid line, there is nice and steep. So it's going fast. A moment later, it's not as steep. It's going slower. A moment after that, it's going even slower. A moment after that, even slower. You see how each one of those slopes is a little bit different? It is, what do we call that? Going from fast to slow. Decelerating. So that means the velocity is changing, specifically decreasing. Decreasing speed. Accelerating. So right here, a little bit of slope. Starts off slow. And then it's going a little bit steeper, so it's going a little bit faster. And then a slightly steeper slope, so it's going even faster. And then a really steep slope. It's going super fast. So what's happening there? Accelerating. The velocity is changing, specifically increasing speed. Last one. How are the motions similar? What is this? What is similar between decelerating and accelerating? The velocity is changing. That's what's similar about accelerating and decelerating. The velocity is changing. So on a position versus time graph, we end up with a curve because the slope on a position versus time graph, class, a position versus time graph. What does the slope tell us? The velocity. So the velocity is changing, the slope is changing. The velocity is changing, the slope is changing. The velocity is decreasing speed or the velocity is increasing speed. The velocity is changing is what's similar about acceleration and deceleration. Cool? All right. Now we want to draw a pair of graphs for each motion. So for the motion of being at rest, draw a position versus time graph and the velocity versus time graph. Okay? So with the position versus time graph, it has to be horizontal. Okay? Any sort of at rest, doesn't really matter where it is. So position could be far from the reference point, it could be close to the reference point. It doesn't matter so long as it is horizontal. But in the velocity versus time graph, velocity is on our y-axis. So if the velocity is 0 is when it's at rest. So this one has to must be on the x-axis. So at rest. Constant positive velocity. That one, it needs to have a positive slope because in a position versus time graph, we need a positive slope for a constant velocity. All right, drawing it simple, just having it starting at the reference point. Not particularly fast, not particularly slow, just a constant velocity. Okay? Same with this one, constant velocity and velocity versus time graph needs to be horizontal. Not too fast, not too slow, somewhere right there in the middle, a constant velocity in a velocity versus time graph. Accelerating in a position versus time graph, accelerating must be curved. So we need to start off with very little slope, and it gets steeper and steeper and steeper and steeper and steeper and steeper. So that is accelerating in a position versus time graph. In a velocity versus time graph, accelerating is going to be a slope, positive slope in this quadrant. Okay, so in this quadrant we have a positive slope for accelerating. Decelerating in a position versus time graph, when you start off with a steep slope, all right, and then it's going to curve to have less slope and less slope, so it's going slower and slower and slower and slower and slower and slower. So decelerating in a positive direction in a position versus time graph. Deceleration velocity versus time graph in the first quadrant here starts with a high velocity and decreasing to a low velocity, down to 0 if you want to, at rest. Being able to pair these graphs is, being able to identify these pairs is essential to being successful on the quiz.